All right, so numbers 1 through 4. Like I said, I think there's probably some value in picking at least one of those to go through. Does anybody have a specific request? 4? Cool. Yeah, that's a good one to hit. All right, so let's go through 4 and 5. Is that cool? Cool. So here we go, number 4. All right, so number 4 says a 5 kilogram, so this is, what do we got? Worksheet 4.1a. So number 4 says a 5 kilogram box is pushed across the table. 5 kilogram box, so you can always start with your force of gravity. Pushed across the table using a force that makes an angle that is 30 degrees below the horizontal. So we're pushing it with some weird force, let's assume that it's Roy, and it tells us that it's at an angle of 30 degrees below the horizontal. Okay? It tells us that the box accelerates at 3 meters a second squared. Almost without thinking, what should I do, you guys? Good. That's huge. That's like mantra in this class. If you know the acceleration, find the net force. So our net force here is going to be mass times acceleration. So we're going to get a net force of 15 newtons. And the force of friction is 10 newtons. Help me out with that, you guys. Which way is the friction going to go?
Left.
Yeah, to the left. Because Roy's pushing it to the right. And so friction has to oppose whatever direction Roy is pushing it, right? Because the motion is going to be in the direction Roy is pushing it. And friction opposes that attempted motion, so friction is going to go the other way. So here's my friction. What kind, you guys? Static or kinetic?
Kinetic.
All right. So, okay. So that's kind of our given information. So let me pause there for a minute. I did that very quickly. Any problems with what I've done so far? Lauren, you good? Everybody's good? All right. Is this an okay drawing? No. Okay, remember, you guys, when you make your free body diagrams to help you solve the problems, I never want to see forces at weird angles like this guy. That's a no-no. All right, so we're going to replace that with the components of that force, right? Okay, so basically, I guess if you wanted, that would look like this. You'd say, all right, well, Roy is pushing this way with some force. That force is at 30 degrees below the horizontal, and so we're going to have a x component of Roy's force and a y component of Roy's force, or y's force. Follow? Okie doke. So let's go over here and make a new free body diagram. So here's my box, 5 kilograms. Gravity's good because that's vertical, so that lies along my coordinates. I'm going to replace this stupid slanty one with the 2 components. So here's the force of Roy in the x direction. Here's the force of Roy in the y direction. I know my friction. There's one other force I have not put in my drawing yet. Normal force. All right, I can't calculate it yet, though, can I? But I could at least describe it. How big is that normal force got to be, you guys? Yeah, it's got to be big enough to cancel these 2 dudes, right? So it's basically just going to be 49 newtons plus whatever the force of Roy in the y direction is. All right? Yeah. Positive, right? Oops. Sorry, I think that's the first time I've ever made absolute value bars in here. But you know what I mean? Like, it needs to be bigger, right? Here. All right, everybody good? Okay. So there's a lot of unknowns here. I don't know the x direction, the y direction, or the normal force. So, thoughts? Triangle? Talk to me more about the triangle. When you say triangle, I assume you mean...
You know that the net force has to be 15.
There you go. Okay, good. Yeah. So when you get stuck like this, ask yourself, you know the net force, is that going to help you at all? So Alex, what are you thinking?
So if it's not going up, and it's up with the cancel, so you can just worry about the left and the right.
Good.
It's just 25. You can do that.
Good. Yeah. All of my motion is going to be horizontal, right? So this acceleration that I found up here is actually horizontal acceleration, right? Because like Alex said, it's not going to go up or down at all. So that means my net force horizontally has got to be 15 newtons, right? So I feel like we should be able to do something with that. So let's see. My net force horizontally is going to be the force of Roy in the x direction plus the force of kinetic friction, right? That's got to add up to 15. So 15 equals the force of Roy in the x direction plus negative 10. Move 10 to both sides, and you get 25 newtons, right? Because then 25 minus 10 gives us 15. Good? All right, so that means that the force of Roy in the x direction is 25 newtons. And so like Ryan said a couple minutes ago, now we have a triangle, we know an angle and a side. So now we can do some trigonometry and figure out the other two sides of the triangle. Questions before I do that? This step is super duper important. Using that net force to find your missing force. Cool? That's, if you know the net force, that's why you know it, so you can find that missing force. Okay, so we can do some trig here. If you divide by the sine of 30, you find out that Roy's force is 29 newtons. So the question said, what's the magnitude of Roy's force? That's what this was asking for. It was asking for how much force is he exerting? I don't care about the direction, just how much. Okay, that's what the word magnitude means. All right, and then the y component here is going to be what, negative 14.5 newtons, I think. So we can put those here, which then means that my or my normal force rather is going to be negative, or 49 plus 14.5, which is what, 63.5? Cool, you guys? Any questions? Going once? Twice? All right, and then the last step asks you to find the coefficient of friction, I think, right? So once you know your force of friction and your normal force, you can find the coefficient by just dividing, right? And just don't forget to drop the negatives. Your coefficient shouldn't be negative. Do we have questions? Lauren, you good?
Yeah, I just made a calculation.
Gotcha.
I had 35 instead of 25.
Oh, gotcha. All right, everybody's happy? Anybody unhappy? Cool. All right. So, number 5. Here's the deal with number 5. In number 4, when you solved this, you split your forces up into components, right? Because the problem was this force, Roy's force, didn't lie along either of my axes, right? So what do I mean when I say axes? Well, in this problem, I mean the x and y-axis, right? Good? So in this problem, when we talk about the x and y-axis, the x-axis means either forward or backward, and the y-axis means either up or down, right? Sorry about the weird yellow. All right, so this is going to seem like a dumb question, but bear with me for a minute. Everybody point for me. In this problem right here, which direction is gravity pulling? Down, right? Down, as in down the y-axis, yes? Okay, keep that in your head for a minute. In this problem, gravity pulls down. And I guess to be fair, gravity always pulls down. But by down, we mean down towards the center of the earth, right? Okay, now, in number 5, you've got a warehouse. So here's the warehouse floor. We'll actually draw the floor. Here's the floor of the warehouse. Okay? And sitting on that floor is a box. All right? And then Roy and his friends get up and they push the box in directions such as east and west and northeast. Okay? So there are a few forces on it. There's force A, which is, I think, 10 newtons. There's force B, which I think was 15 newtons that way. And there's force C, which I think is also 15 newtons, but it's at some stupid angle. So what direction was force A in, you guys? Due north. So in this problem, my y-axis no longer means up and down. It means north, and south. And my x-axis doesn't mean forward and backwards, it means east and west, right? Good? Point for me. In this problem, which way is gravity pulling the box?
That way.
Yeah, this way, right? We're above the box looking down on it. We're like up here looking down on the box, right? That's what this drawing represents. Okay? So gravity is pulling the box into the floor. Good? That's a pain to draw because you can't draw an arrow pointing into the board. But we don't need to worry about it in this problem because there's a normal force that's going to cancel it out. Make sense? So you do not need to draw gravity in this problem because it's just going to get canceled out anyway.
Why not so you cancel out?
Because it tells you it's sitting on a warehouse floor, tells you it's frictionless, it's not going to move up or down. All of its motion is going to be north, south, east, or west, or some weird combination of them. You know what I mean? Everybody good? Okay. So, this is what I call a top view problem. All right? The first problem on your homework tonight is another one of these. Okay? In some sense, they're easier. You don't need to worry about gravity. They're, like, honestly, this problem you could have done in, what was our vector chapter? Was that chapter 2? Whatever vector chapter was. That's all this is. This is just vector addition with one little add-on at the end. Okay? So, let's run through the solution. That is not what I wanted to happen. That is what I wanted to happen. Okay, so let's make a new free body diagram. So the problem is this stupid force of C doesn't lie along either of our axes, right? So you got to find the components. So here's force C, 15 newtons. Do a little bit of trig. We know this is 30 degrees. And find your components. The force of C in the y direction ends up being 7.5. Force of C in the x direction ends up being, it's like 12.9. Let's just call it 13 newtons. Good? Okay, so here we go. Let's make a new drawing. Here's our box. Here's our forces. Force A, 10 newtons. Force B, negative 15 newtons. Force C in the y direction, 7.5. Force C in the x direction, 13. Did I do that too quick? All right. Back in our vectors chapter, here's how we would have done this. We would have said there's three forces. There's force A, B, and C. I want to find the resultant net force. Each of those forces has an x and a y component, right? So, what's the x component of force A, you guys? Force A goes straight north. So the x component is 0 and the y component's 10, right? Force B has an x component of negative 15 and a y component of 0. And then force C has an x component of 13 and a y component of 7.5. So add them up. 15 and 13, or negative 15 and 13 gives you negative 2. Y component is 17.5. Just like if we added up our x's and added up our y's. Make sense? So whether you make the drawing or the chart or both, I don't care. Probably had to make at least one of them. Good? And then we're almost done. Because now what I can do is I can go, oh, well that means that my net force in the x direction is negative 2. My net force in the y direction is 17.5. Net force in the x direction, negative 2. Net force in the y direction, 17.5. Notice, how did I draw those two components? Okay, I head to tail. And then I can find my net force. How do I do it? Pythagorean theorem, right? 2 squared, 17.5 squared, square root it. You get 17.6 newtons. Am I done? Nope. You got to find the angle. And you get 83 degrees north of west, right? And Alex is right now going, that's not the answer on the sheet, right? So let me pause for a minute. That is not the answer on the sheet. We are not done. Questions?
Well, okay, I'll ask.
You sure? Okay. Are there questions about how I got up to here? We good? Milena, you okay?
Yeah.
Yeah? Everybody good? Drew, you good? Yes. You good? Cool. I don't know why I answered that question for you. Joey, you good? Everybody's good? All right, cool. The question didn't ask for net force. What's it ask for? Acceleration. So you got to go one more step. All right, everybody, I want everybody to listen to this, even if you got it right. This is a thing that I've mentioned before, but this is the first time it has become super duper important. Acceleration is vector, which means it has direction. All right? It turns out that the direction of the acceleration is always, without exception, the same as the direction of the net force. Okay? That's what one of the things Newton's second law tells us. The acceleration is in the same direction as the net force. Hello, Miss Becker. Instructing? I am, yes. Why? What's up? Yeah, sure. Yeah, bye. Okay. So, your net force is in the same direction as the acceleration. So, last step, we know the acceleration, net force over mass. Net force was what, 17.6. Mass is 0.8. Divide it out, you get 22 meters a second squared. And then the direction is the same as the net force. Yeah.
We can do the same thing every time if we do like acceleration x and acceleration y.
Yeah. Good, you guys?
It's positive north or west, or
Positive because it's not along x or y axis, so it's always going to be positive. And then the direction is described using an angle, not just using positive or negative. Saying west takes care of the negative you're thinking of.
yeah, so would the exception be here?
So it's
Oh, okay.
at 83 degrees north of west. Make sense? Everybody good? Questions? Issues? Concerns? Anything? All right, so real quick on the homework tonight, question number 6, the wording on it is terrible. It says that he wants to move it in the right direction, by which I meant to the right, but it's worded horribly. The kid is trying to make the box move to the east. So what's the minimum force he needs? Okay? In number 8, the 345 newtons in that problem is the force being exerted on the dude's shoelaces. Okay? In part B, for some random reason, the guy's name changes from Roy to Robert, and instead of him being beat up by the mob, he's being beat up by the cops. I don't know how that changed. I apologize. There was nothing. I don't know. I think it might have been a part C, and I don't know. Anyway, it's all the same person and the same bad guys. Good? Okay, cool. Let me know how I can help you. You got half an hour to work. 2 seconds. The dean, who's one of the secretaries in the front office, wants to see you about something. I'm not sure what. Yeah, you might want to. I don't know what it was about. It didn't sound serious. Yeah. Oh, let me stop recording.